Okay, in this video, I'm going to go over three types of optimization models that are operation optimization models that are operations related. In my mind, they get more difficult as we move on, and the last one will be a great introduction. The inventory one will be a good introduction to the model that I want to talk about that comes out of Chapter 8, multi-period planning. So I think I'm going to do this in probably two videos. I'll try to cover the product mix and the blending problem in this video, and then another video for the inventory. And you don't have to do these for homework. These are just getting you used to thinking about optimization in Excel for three different types of operation problems. The product mix, the concept is that there are products that we need to make, but we have limited resources, so we want the model to determine which products to choose to make and how much based on our limited resources, and we're usually trying to maximize profit. A blending problem is like a gasoline problem or developing a vitamin or a diet, and there's a certain type of product that we're trying to prepare, and we've got to have certain ingredients, and we're buying raw materials that have different percentages of these ingredients, and we need to know which of these raw materials to purchase so that we hit our daily requirements, our daily minimums, and do it in the cheapest way. And then the inventory, the concept is that we have demand over time, and we have different ways to try to meet demand. And in that case, sometimes we need to buy or build earlier than the demand and carry inventory from one period to the next. So let's jump into Excel, and I'll make these problems available to you. This file, it's called OEM optimization models. And again, these are not required. You're not going to need to do homework on these. These are just getting you used to thinking about optimization in a spreadsheet and going through the steps. So here's the thought. We've got six products. Each of them, someone has already done the hard work and determined what the profit is per unit. So that's the most profitable one per unit, is that every time we make one, the assumption is that we're going to be able to sell it and make $45 in profit. So the question is, how many of each of these products to make to maximize some profit? And you can see the profit formula is a formula as a function of the unit profit and how many we make. Well, product one requires all of these products require resources. For example, product one requires 1 unit of steel, 4 units of wood, no plastic, no 2 rubbers, 2 types of rubber, 2 glasses, and 1 paint. So when I look at the usage of steel, it's going to be how much of each of these that we make multiplied by the different steel requirements for each of these products. So this is a usage formula. And the idea is that we're limited by these. The steel is limited by 800. This is how many we have. So we have to make sure that we choose products so that these don't exceed these, and we're trying to make this as big as possible. So in optimization speak, these are our decision variables. This is my objective function, and then I have 6 different types of constraints. Now I could play with these. I could say, well, let's maximize this since it's 45. So I'm going to make 10, and that's plenty. Let me make 500, and you can see that's too many. So that's starting to look, and that looks like that's okay. Maybe I make 150 more, and all I'm doing is looking at this. There's my profit, and I'm looking at usage over here. And as long as these numbers are less than these, I'm cool. 175. Looks like I can go a little bit more. Maybe another, maybe 275. No. 200. There you go. 200. 200. And I've maxed out on this. So I can't make any more product 2 because I'm going to exceed that. I've exhausted all this. So the only other product I can consider making is product 3 because it doesn't use any steel. I can look at this, and so I can bump this up. And all I'm doing is putting my eyeballs and looking at these numbers against this one. So I could put this and say, well, what if I do 50 of those? That's getting close. I think I can go maybe another 3. That's pretty well lit. Maybe 53 and some fractions. There you go. And I've maxed out on these, and I'm still okay on these other ones. So what would be next product? I can't use anything that requires steel or wood. So I could look at product 4. That might be one. No, yeah, product 4 would be one I could consider adding because I don't need any of that. So here you go, on and on and on. Keep adding. Well, that's one way to do it. And even if I follow this strategy, there's no guarantee that this mix is the optimal. So what I've done is use solver. Look how this is structured. Cell A3 I'm trying to maximize. The cells I'm trying to change are my decision variables, and then I've added a set of constraints. These are actually 6 different constraints. So let me get rid of this and add them again. And I'm going to add a set of constraints saying that in this array, in this vector of 6 values, they are paired with these 6. So I'm going to say that this set has to be less than or equal to this set, and that's each pair, there's a constraint. So it's actually 6 constraints I've written. And then the last one, I can't make negative products, and I'm going to use this, and so I'm going to solve it. And look at that. It finds a solution. There's the profit. Here's the product mix. I can look over here and see I'm tapped out on everything except glass. Glass is the only thing that I did not exhaust with this particular mix. So it would be profitable to add additional inventories of everything but glass. Glass doesn't do me any good. And that's the product mix. And if you notice, product 2 is not even included. So intuition or greedy algorithms aren't always the best. Let's go to the second one. This is a blending problem. And what we're trying to do is determine these 4 raw materials to buy. So I'm going to go to a feed store, and I'm going to, I think this is a feed for livestock, and I'm going to buy some of this. I'm going to buy this, and I'm going to build a food source that I'm going to feed my livestock. And this is what these cost per some unit of quantity. And if I buy nutrient 1, this is what it cost, and this is how much of the vitamins or these nutrients that they have. And if you notice that nutrient D has an incredible really shows up primarily in 3 and 4, but they're the most expensive. So the trick is, what is the percentage breakdown of each of these nutrients so that I hit my minimum requirements, and I'm trying to do this in the cheapest possible way. You've got to make sure this sums to 100, so this has to be equal to 100%. The nutrients supplied has to be greater than or equal to this. So if we look at, again, solver, setting this up, I'm trying to minimize my cost by changing these variables, these percentages. And then I've got one set of constraints. That one constraint that says that the sum, which is in cell G16, has to equal to 1. So I'm building a standard unit. And then I've got these sets of constraints that I've got to meet my requirements, my daily minimums. Turn this into a linear solution. Solve it. It finds a solution. And there is your breakdown. It wants to use a lot of this, a lot of this, and a little bit of this. And that is the cheapest per bushel or per quantity. And you can see we've met the daily requirements. They may have been exceeded on a couple of these. These are not. These are well over. These are the ones that are causing us problems. And keep in mind that these solutions are if everything is linear, you can't beat this answer. You may tie it, but you can't beat it. You might come up with a different percentage that will give you a number that's the same, but you are certainly not going to beat it. Okay, I'll do one more video going over the inventory problem. Thanks.